LIS 754, Systems Analysis and Design, Systems Thinking. In this session, we're going to talk about systems theory and complexity in systems. When we think about systems theory, we're going to be thinking about the parts of a system, the sum of those parts, and the relationships between the parts, and the implications of systems. We're going to think about complexity in systems, particularly in problem analysis and in systems thinking. So let's first define what a system is. A system is a set of components. Components will interact with each other. They may or may not be independent or interdependent between them. These components form a whole. The relationships between the different components can be different from each other. Different components can relate to other systems. So we can see how we can get a very complex set of components and relationships pretty quickly. This system can be a natural system like biological systems like the rainforest. These systems can be human systems. They can be computer systems. So systems theory is the idea that everything can be seen as a web of relationships. And that there are all these different components in a system, and that we can know them, that these are knowable. Systems have common patterns, behaviors, and properties that can be understood and used to develop greater insight into the behavior of this complex phenomenon. There are three primary components in all systems. There is input, there's the process, and the output. And these components are the basis of every system. But they don't live in isolation, these components. There are environments, the context in which this system exists, and there are feedback loops. So output becomes input. And this happens in biologic systems, so things in the rainforest, when leaves fall, they deteriorate and become part of the dirt. The output becomes part of the input to nourish the trees that create the conditions. So systems are complex at some level and at their but are also very simple at their most basic. Input, process, output. But also implied are things like control. So control is, especially in human systems and in biological systems and others as well, things that keep the process in check. So in a computer system, we think of those things as edits, or we think of those things as errors. If somebody puts the wrong input in, it's going to cause an unsatisfactory processing step. So we want to make sure that we know that there are more things than just beside input, outputs, and processes. And boundaries and interface. So where does this system end, one system end and the other begin? And what are the points of connection between different systems? So it's not a far leap from systems theory to systems thinking. Systems are made of parts. Parts interact with each other. The relationships between these different parts are dynamic. And we can see how that would work if we thought of something like a city. So I live in an apartment. My apartment is part of an apartment building. My building is on a block with other buildings. My block is within a township. The township is within a city. The city is within a state. within a county, the county is in a state, the state is within a nation. And all of those places interact with each other, and we can see interfaces in how the roads work, we can see interfaces in how the power grid works, we can see and imagine interfaces in how water delivery works. So we see that complexity in cities and in technology. But we know that how these different components work. If something goes wrong in my apartment building, it will affect the people in my building. If something goes wrong in the block, it affects that. But if things keep cascading, then we have bigger and bigger problems. And that was one of the issues that caused the great blackout on the East Coast a number of years ago, are those kinds of rolling problems where it rolled up the chain of the systems, where one failure caused failures in other points. And that kind of is a system effect. One of the really interesting issues about systems, whether computerized or biologic or human, is the issue of identifying problems. We can think about doing analysis, and which is what we're doing in this course. We can look at issues, try to find the points of connection. We can use communication to gather up information, use our intuition to figure out which is the most important pieces. And we can be creative in the problem solving, and we can have very clear boundaries, but still not be solving the right problems. And I'd like to tell a little story about an experience I had when I worked for a library systems vendor. We were rewriting the circulation system, and I was working with the user group and managing the software development process, and we developed this really terrific billing system. So we had a lot of issues with the old billing system. People didn't like it, especially large academic libraries had some real problems with it. And so we took all of the problem reports that we were given and we compared it to what the system did, and we came up with this terrific billing system. I had worked in insurance companies, and I will tell you, insurance companies really know how to bill people for money. And so we had this great system. And I presented it to this user group, and they sat there, sort of when I was done, they sat there in stunned silence, and I wondered what was going on. And one man spoke up and said, "Stacy, we want the book back." And I was totally taken aback by that. We read all those problem reports, we processed all the issues that were given to us and all the complaints, and the problem was always with money, but he was really right. He saw through the problem that they didn't need this huge, complex system. They really were trying to get the book back. And so I have taken that as a really, as a real lesson to myself about making sure that I really understand that problem, that I look for that hidden component that can get lost in all the words, and even yeah. So anyway, that's I have that story has stuck with me for the last. It's been a long time, and I find that to be for me to be really important. We want the book back. So if we're looking at systems and looking at how our new systems will fit into an existing context, we need to evaluate the system and what this new system or what this change to an existing system will do to the entire ecosystem of our organization, of our community. And so understanding the conditions and dynamics of a system before we make changes is really important. And one of the things that we're actually trying to do in our analysis in this is to capture the system relationships. And we want to be able to explore those by multiple perspectives. So when we are thinking about doing a systems intervention, and our new systems will actually be interventions. We want to make sure that we are evaluating our interventions. I really love this sentence, this little segment here, evaluating misaligned interventions, making sure that what we do lines up with everything else. If they don't align, we're going to have problems. And of course, we want to look at our intended users and the purposes of our new system. So you may be thinking, if I have a new system, how is that a system change? Well, if we consider something like Sarah's project, which is going to be new functionality in a law firm, that law firm already is a system, and adding this new software that's going to allow for easier exchange of information, for being able to retrieve information that previously wasn't able to be retrieved. It's going to change perceptions. It's going to change the information flow. It's going to change all of the current ways that people think about getting information. If we think about Mosie's project and the memorial site, we can see how that will affect not just the library in their ecosystem, but the entire community. And so understanding those, thinking of our actions as an intervention in an existing system is an important process. And we've already started some of that thinking. I really like this diagram. In a number of papers that I have read on systems thinking, they pose it as being opposite of scientific thinking. And I had a hard time with that because I didn't agree with that. I thought that it was a more holistic process. And this drawing supports that. So we can think of systems thinking skills as being able to integrate all the different types of thinking that we currently discuss when talking about problem solving and those kinds of issues. And so we can think of such opposite kinds of processes as operational thinking. So thinking through what are all the steps of the processes that happen right now. With nonlinear thinking, which is really looking at not so much looking at the relationships nearest to each of those objects, but thinking in a more circular or less operational way. And we have scientific thinking, looking for quantities and measures and being able to formulate and test hypotheses like the scientific method. With creative thinking, being more artistic, being more trying to combine your left brain and your right brain sight, as well as looking at the details, looking at the big view, and looking at the dynamics of the different components. There are several other videos about systems thinking on the website. There are a bunch of them on YouTube. If this is something that's interesting to you, you can look for. There's a lot written on it. It's usually written for more in a business-oriented process. There is a whole language and a whole way of annotating more systematic analysis. But I want us to think in our projects, to be able to think of our projects as a system within larger systems, within different contexts, and to be able to use all these different kinds of skills, thinking skills, in our projects. Our next session will be on project management. There are slides, videos, and readings up on the Canvas site. Talk to you soon.